Hey, Global Impact students, this is Mr. Ellinger. This lesson is on modeling with quadratic functions. Our learning target for the lesson is we want to be able to model data with quadratic functions. So we've already talked about modeling data with linear functions. So now we're going to look at modeling data with nonlinear functions, and our first one is a quadratic function. Some essential understanding for you for the lesson: 3 non-collinear points, no two of which are in line vertically, are on the graph of exactly one quadratic function. Remember, non-collinear means 3 points not on the same line. Standard form is calculator ready. Background knowledge for the lesson: we should know that 2 points determine a line. The first essential understanding extends this property. Since the points are on exactly one quadratic function, the 3 points determine this function. In this lesson, we will use the 3 points to write and solve a system of linear equations. This same method will be used to find a quadratic model for real-world data. Be sure that a quadratic model can apply to a data set that contains more than 3 points. Be aware that a quadratic model can apply to a data set that contains more than 3 points. A quadratic model for 3 points is an exact fit, while a model for more than 3 points may be only an approximation. However, in some cases, a quadratic function is the exact fit for more than 3 data points. So basically what that's saying is if we're going to try to model a set of data with an equation, then we need 3 points. We need to have 3 non-collinear points to determine the model of our data. And again, I'm going to compare this back to linear functions. When we had linear functions, we needed 2 points to write an equation, because in order to write an equation, a regression model for a set of data, we have to know the slope of our regression line or our trend line. And the only way that you could get the slope of that line was to use 2 points. Here we have to use 3 points. And if you think about why that is, if I only use 2 points, the property is between 2 points we can draw a line. Okay, so if you only use 2, you're just going to get a linear model. So we need that third point, and we need it to be non-collinear with the first 2, so that we can see the curve. Okay, so first of all, we have to know that the data is nonlinear, and the 3 points that we use to generate our model have to be non-collinear. So we know the vertex and a point on a parabola. You can use vertex form to write an equation of the parabola. If you do not know the vertex, you can use standard form and any 3 points of the parabola to find an equation. 3 non-collinear points, no 2 of which are in line vertically, are on the graph of exactly one quadratic function. So here we have an example. A parabola contains the points 0, 0, -1, -2, and 1, 6. What is the equation of this parabola in standard form? So what we can do here is we can substitute the x, y values into our standard form, and we are going to write a system of equations. So here's how this works. If I use 0, 0 first, just substitute 0 in for x, all our x's, and 0 in for y, and simplify this down, we get an equation that's c equals 0. If we use -1, -2 and do the exact same thing, substitute in -1 for x, -2 for y, we get an equation that states -2 equals a minus b plus c. And then when we do that same thing for 1, 6, substitute 1 in for x, 6 in for y, we get an equation of 6 equals a plus b plus c. So you'll notice that we have 2 equations that have a, b's, and c's in them. And then we have this other equation that's actually very nice for this case, that c equals 0. So what we can do in our other 2 equations is we can substitute 0 in for c, which will leave a system of a minus b equals -2 and a plus b equals 6. And we can use elimination here to solve this system. And when we do that, we get a equals 2 and b equals 4, and then add in that c equals 0. Put those back into standard form, so we get an equation of y equals 2x plus 2. We get an equation of y equals 2x squared plus 4x plus 0, or y equals 2x squared plus 4x. We don't need the 0 in there. So that's the equation of the parabola that contains the given points. So there is a trick there, all right? There's a trick. We got 3 points on our parabola. We need the equation of the parabola. Use the form, okay? A lot of times we focus on using the coefficients A, B, and C to do all of our stuff, but we don't know A, B, and C from the information, so we have to be a little bit creative, okay? And we do this a little bit when we're talking about linear equations, but we have other tricks that aren't so difficult to use to generate our equations in a different way. But this is how we do this algebraically, okay? Using these relationships between x and y. We have three relations here, okay? 3 points in this relation. So this is where that relationship idea comes into play. We know that this relation holds true, 0, 0, -1, -2, 1, 6. Forever, whatever our equation winds up being, those three values are related in that way. So we use that relationship in a different way to come up with our equation, okay? So we can write equations in standard form if we just have three random points that are on the parabola. So that's kind of a cool thing. Okay, so here, let's take a look at application of this. Here we have a physics problem. Campers at an aerospace camp launch rockets on the last day of camp. The path of rocket 1 is modeled by the equation h equals -16t squared plus 150t plus 1, where t is the time in seconds and h is the distance from the ground. The path of rocket 2 is modeled by the graph at the right. Which rocket flew higher? Well, you know, it's nice we can actually tell the height of rocket 2 just from the graph, but the problem is rocket 1 is not given to us in a graph. So what we do is we say, all right, for rocket 1, the maximum height of rocket 1 is at the vertex of the parabola. So we just have to go ahead and determine that vertex. So we use our formula -b/2a, and here we have our calculation of this. And so the vertex of the parabola of rocket 1 would be given by the point 4.7 and then 352.6. So the maximum height of rocket 1 is 352.6. So there's rocket 1. Let's take a look at rocket 2. The maximum height of rocket 2 is at the vertex of the parabola. You can use the graph to find the approximate maximum height of the rocket. So it's nice we can see approximately what the height is. Okay, but we can also say, all right, well, rocket 1, what was the height? 352.6? Yeah. So rocket 1 was 352.6. Since it's not even close here, 580, even if we didn't know that it was exactly 580, clearly rocket 2's height was much higher than rocket 1's. So we just to answer the question, we could say that rocket 2 flew much higher than rocket 1. Now, here's a different question. Which rocket stayed in the air longer? Well, if you think about that, how would we go ahead and determine that? Well, here the graph of rocket 2 can help us that. That value is actually right here, okay? The rocket is launched at time 0, height 0. It's launched, it reaches a maximum height of 580 after 6 seconds, and then it starts to come back down towards the ground. So where our parabola hits the x-axis again, remember x-axis, y is 0, y is the height here, so the height is 0 at this value again, so this is the rocket has come back down to the ground. So at 12 seconds, it looks like that the rocket is completed its flight. So for rocket 2, the time that it was in the air, the travel was 12 seconds. All right, now let's go back to rocket 1. Rocket 1, how are we going to figure this out for rocket 1? The vertex is going to be a big clue. Okay, now I'm going to draw a graph here, and it's going to be very crude, but it will prove the point. All right, so here, let's just say that this was the graph of rocket 1. Okay, so it's launched at 0, 0. It reaches its max height at, let's say it's right here, at 4.7. Okay, 352.6. And we want to know what's that x-coordinate. If we can find that x-coordinate, that's what we need to answer the question and compare to rocket 2, right? So how do we determine that? Well, again, remember, parabolas are symmetric. So if I drop my axis of symmetry down here through the vertex, how far is it on the graph from our 0, 0 to this axis of symmetry? 4.7. How far is it from the axis of symmetry over to this point where the graph hits the x-axis again? That's 4.7. So rocket 1 was in the air for 9.4 seconds. So I can go back and compare that. Rocket 1, 9.4 seconds. So rocket 2 was in the air longer, about 3 seconds longer. So it flew higher, it was in the air longer, kind of makes sense. That's probably what we would expect, okay? Question B, what is the reasonable domain and range for each quadratic model? Okay, now remember, reasonable domain is taking into account the context of the problem. You know, our models, our graphs, really these parabolas, like in this graph up here, the graph continues on forever below the x-axis. Our function, or equation back that we had, h equals negative 16t squared plus 150t plus 1, if I graph that, you know, that's a parabola that has just itself, just the equation, has an infinite domain, and its range is infinite as well. It would have a maximum value, but for the problem, remember, for the problem, that's the reasonable domain. So the reasonable domain in this problem would be, and again, for the model is the one that we have the graph of, the reasonable domain would be from 0 to 12. Including 0 and 12, this would be the domain. Okay, and this is for rocket 2. What's the range? Well, the range, what's the least range value? This is 0 again. And the max range value would be 580. So that's the reasonable domain and range for the problem. X can be, or in this case, S could be anywhere between 0 and 12 because that's the only time that the rocket's actually in flight. And then the range would be anywhere from 0 to 580 because it can't go below 0 distance off the ground, and the maximum value was 580. Okay, so describe what the domains tell you about each of the models and why the domains or models for the models are different. Well, the model of, again, this was rocket 2. Rocket 1's domain would be what? 0 to 9.4. That's how long it was in the air. And the reason that their domains are different is because, like I just said, rocket 1 was only in the air for 9.4 seconds. So its domain, its S value, its time value should only go from 0 to 9.4. It doesn't make any sense to look at anything past 9.4 because the thing had already come back and hit the ground. Rocket 2, again, was in the air for 12 seconds, so it doesn't make sense to look at anything beyond 12 seconds. We're only concerned with what happened between time 0 and time 12. And in rocket 1, from time 0 to time 9.4. Okay, so domain and range has context. Domain and range limits or narrows our scope of a problem when we're looking at a real world problem like this. Okay, so that's the application of domain and range. So here again, modeling. We're going to do a lot of modeling. We're going to do a lot of application. So this is good stuff here. All right, so I will see you guys next time. Hope you have a great day.